Plastic injection molding was developed to save the African elephant from extinction. Ivory from their tusks was used to create billiard balls, but when the ivory became scarce, manufacturers offered a $10,000 reward for a replacement. In response, John Wesley Hyatt and his brother Isaiah created one of the first plastics, celluloid, and in 1847 they also patented a process for injecting the polymer into a mold. This device was the precursor to the modern-day plastic injection molding machine. Today, plastic injection molding is by far the most popular fabrication process for mass-producing plastic products. Virtually all plastic objects you encounter were injection molded, including remote control cases, cutlery, chairs, and Lego bricks. In principle, injection molding is simple. You melt plastic, inject it into a mold, it cools, and out comes your plastic product. In reality, injection molding is an intricate and complex process. An injection molding machine has three main parts: the injection unit, the mold, and the clamp. Plastic pellets in the hopper feed into the barrel of the injection unit. Inside the barrel, a screw transports the pellets forward. Heater bands wrapped around the outside of the barrel help maintain an elevated temperature inside the barrel. As the pellets are moved forward by the screw, they gradually melt and are entirely molten by the time they reach the front of the barrel. The screw is rammed forward, acting like a syringe plunger, and injects molten plastic into the mold. The plastic rapidly cools, and when it is completely solidified, the mold opens and the part is ejected. The mold then closes, and the process repeats. All injection molded objects start with these plastic pellets, several millimeters in diameter. They can be mixed with recycled material or colorant, then fed into the injection molded machine. Before the mid-20th century, injection molding machines relied on external heating of the barrel to melt the plastic before a simple plunger injected the molten material. However, plastic is a poor conductor of heat, which results in uneven heating of the material. Either the middle was too cool and not fully melted, or the outer regions were too hot and began to degrade. The solution was this, often regarded as the most important contribution that revolutionized the plastic industry in the 20th century. In older plunger-style machines, plastic filled a cylindrical shape in the barrel. But because the screw has a central shaft, the plastic fits around the shaft, filling it in an annular shape inside the barrel. This means heat doesn't travel as far and the plastic is heated more evenly. The screw also has flights wrapped around the shaft. As the screw rotates, the flights push the raw material forward through the barrel. The flights also induce mixing of the plastic. This mixing homogenizes the melt, distributing heat and colorant evenly. Now the screw has an even more important function. As you move along the length of the screw, the shaft gradually increases in diameter. This means the available space for the plastic decreases as it moves forward. So the plastic pellets are rubbed together, which squeezes out air and shears the pellets against each other in the wall of the barrel. The shearing action creates friction and therefore heat, which contributes to the melting of the plastic. In fact, the screw-induced shear supplies a majority of the heat needed to melt the plastic, with the rest being supplied by the heater bands. After the plastic is melted and pushed in front of the screw is rammed forward like a plunger injecting the plastic into the mold. To prevent the plastic from flowing backwards, the screw contains a one-way valve called a check ring. When the screw turns, material pushes the check ring forward. In this position, indentation or flutes in the screw head allow the passage of material. When the screw pushes forward, the check ring is shoved back up against the thrust ring. This prevents plastic from moving backwards, and thus it must move into the mold. After plastic injects into the mold, it must then solidify. To speed up the cooling process, coolant, typically water, is piped through channels inside the mold just beneath the interior surface. The water is colder than the molten plastic and so absorbs heat from the mold. After the injected part has solidified, the mold opens. When initially opening the mold, you are increasing the volume without introducing any air. This creates a vacuum and a suction force that holds the mold together. So the mold opens in two stages. First, it slowly opens several millimeters to allow air to rush in and break the vacuum. Then, the mold quickly opens the rest of the way so the part can be removed. The empty space inside the mold that is in the shape of the part to be produced is called the cavity image. The plastic needs to get from the nozzle of the injection unit to the cavity image and gets there via a tunnel called the sprue bushing. Plastic inside the bushing solidifies attached to the part and is called the sprue. Sprues are manually twisted or cut off the part in a finishing process. For example, on the underside of this plastic chair, you can see the knob, which is the remnant of a sprue. All the plastic in this chair was injected from this point. Sprues are attached to objects made in single cavity molds. That is, a mold where only one part is made every injection cycle. Smaller objects are made in multiples in a single mold. In these multi-cavity molds, the sprue connects not to the part itself, but to a network of distribution tunnels called runners. The runners fan out from the sprue and connect to each cavity in the mold via a small, typically rectangular entrance called the gate. If you look closely at these pieces of plastic cutlery, you can see the location of the gate. The parts for model planes typically come still attached to the runners and gates. Molds always have at least two parts, and where the parts of the mold meet is called the parting line. If you look closely, you can see the parting line on injected molded objects. Here, on this piece of cutlery, you can see the parting line along the side of the fork. When mold halves close, they are never perfectly aligned, nor are they perfectly sharp corners. This will result in a noticeable parting line on the molded object. Removing the part from the mold is not as easy as it seems. When the plastic cools, it shrinks and so becomes stuck tightly on the core half of the mold. Molds have built-in ejector pins that push the part off the mold. The ends of the pins sit flush with the core half of the mold, but are not perfect. Sometimes they protrude or are indented slightly. So if you look closely, you will see circular ejector pin witness marks on molded products. Here they are on this plastic knife, and there are an array of witness marks on this plastic chair. Another very important aspect of mold design is the draft angle. If a part has walls that are exactly 90 degrees, it will be very difficult to eject for a number of reasons. When the part is ejected, its inner walls will scrape against the core half of the mold. Also, a vacuum will be created since air cannot enter. However, if the walls are slightly tapered, even just 1 or 2 degrees, it becomes much easier for the part to be removed. Because once the part is moved just slightly, the walls are no longer in contact with the cavity and air can rush in. One truly impressive example of injection molding is the Lego brick. You can see the injection point in the middle of the stud. But this is not from a gate or a sprue. The Lego molds inject plastic into cavities using hot runners. With hot runners, the distribution network is heated and stays molten. This means the molded bricks are ejected in a ready-to-use state because they do not have to be manually removed from gates or sprues. Hot runners also result in a more subtle blemish at the injection point. The downside is that this setup is much more expensive than a traditional cold runner system. If you look closely, you can see the ejector pin witness marks on the bottom edges of the brick. If you cut a Lego brick in half, you can see that these inner supports are thicker at the top than at the bottom. There's a draft angle of about 1.5 degrees. This helps the ejector pins push the brick off the mold. How many injection molded items can you identify? Can you see the ejector pin witness marks and parting lines? Can you find out where the injection point of the plastic is? I'm pretty sure if you look for these clues, you'll find that you are in a world utterly filled with plastic injection molded objects. I'm Bill Hammack, the Engineer Guy.